So I can now apply the conservation of mechanical energy, because I know what the velocity is at any angle of theta, and I know what the potential energy is. So let the total energy be just the mechanical energy, which depends on my initial conditions wherever I start. Maybe it's just that I release it here with 0 speed, maybe I give it a little speed. It is a number, it is a constant. So that is going to be 1/2 mv squared at a random angle of theta, and that means this is v, so that is r squared times theta dot squared. This is simply 1/2 m v squared, nothing else. So this is the kinetic energy. Plus the potential energy, which is mg times r times 1 minus cosine theta. And this is always the same, independent of the angle of theta, because gravity is a conservative force. So this is the conservation of mechanical energy. This angle cosine theta is really a pain in the neck. And therefore, what we're going to do is something we have seen before. We're going to make a small angle approximation. Small angle approximation. And we're going to write for cosine theta 1 minus theta squared divided by 2. That is a very, very good approximation. That approximation is way better than the one we did before, when we simply said the cosine of theta equals 1. Remember we did that once? We said, oh, for theta is very small, the cosine of theta is about 1. If we did that now, we would be dead in the waters. Because if we said the cosine of theta is 1, this becomes 0, and you end up with nonsense. Because it would say that the mechanical energy is changing all the time, because this velocity is changing all the time. So we cannot do that. We would kill ourselves if we did that. The approximation is really amazingly good. If I give you here theta in radians, and I give you here the cosine of theta, and here I give you 1 minus theta squared over 2, then if I take 1/60th of a radian, and I pick 1/60th, since this is approximately 1 degree, but I pick exactly 1/60th, and I ask what the cosine is, that is 0.999, and then I have an 8.61114. Just use my calculator. Then I calculate what 1 minus theta squared over 2 is, and I find 0.999861111. That is very, very close. That only differs by 3 parts in a billion. That is very close. That means the difference between the two is only 1/3 of a millionth of a percent. Suppose now I go a little rougher, and I go to 1/5 of a radian, which is about 12 degrees. So this is very roughly 12 degrees. Then the cosine of theta equals 0.98007, and 1 minus theta squared over 2 equals 0.98000. So that still is amazingly close. That is only differs by 7 parts in 100,000. So the difference is less than 1/100th of a percent. So with this in mind, I feel comfortable to pursue my conservation of mechanical energy, and I'm going to replace this cosine theta by 1 minus theta squared divided by 2. So I will continue here. Center blackboard is always nice. You can see it best. And I will massage that equation a little further. And of course, you can already guess what I'm going to do when I massage it a little further. I'm going to take the time derivative, just as I did in the case of the spring. So we're going to get that the mechanical energy, which is not changing, equals 1/2 m r squared theta dot squared plus mgr. Cosine squared becomes 1 minus theta squared over 2. So we have a minus times minus becomes plus. So I get simply theta squared over 2. And now I take the time derivative. So this becomes 0 equals. Now, I get a 2 out of here, which eats up this 1/2. So I get m r squared. Then I get theta dot, but the chain rule gives me a theta double dot. Excuse me? Anything wrong? I don't think so. Thank you. So, I have to take the derivative of this one. The 2 flips out, which eats up this 2. So I get mgr, and then I get a theta, but the chain rule gives me a theta dot. I lose my m. I lose 1r. I lose my theta dot. I picked the wrong one. I lose my theta dot, not the theta. And what do I find? That theta double dot plus g over r times theta equals 0. And I couldn't be happier, because this tells me that the motion is that of a simple harmonic oscillation. And the solution is theta equals some maximum angle for theta, which is the amplitude in angle, times the cosine of omega t plus phi. This is the angular frequency, has nothing to do with that omega there, which is the angular velocity, which is changing in time. This is a constant, this is angular frequency, and this omega equals the square root of g over r. And so the period of the oscillation is 2 pi times the square root of r over g. And when you see that, you say, hey, Populape, I have seen that before. Where have we seen this before? Almost a carbon copy of something that we have seen before. What is it? Excuse me, speak louder. Pendulum. We had a pendulum whereby we had length L of a massless string. We had an object M hanging on the end. And what was it doing? It was going along a perfect arc, which is exactly identical. The problem is the same. It's not a surprise, because now we have a surface, which is an exact perfect arc. It's a circle. We have no friction. We assumed with the pendulum that there was no friction either. So it shouldn't surprise us that you get exactly the same period that you had with a pendulum, and except that, of course, with the pendulum, what we called L is now